Hello?
Hello. Yeah. Did you guys try some questions from the problems I'd sent?
Yes.
Tell me which ones, if you have not gotten some question.
Uh, yeah.
Or which ones you tried but you couldn't get it at the end or something like that.
Yeah, so that question.
Okay, actually before that, let me know like which did you get any questions?
Uh, I got question one,
What is the answer for one?
uh, 1850.
That is correct.
And
Do you
then,
know what is the logic? What did you do?
if I just, I get this new.
N minus
So,
86 and
uh,
n plus 86 are both perfect squares.
yeah, so then you could say that there are integers k squared and k squared plus 172,
Mm-hmm.
and that k squared plus 172 must be a square itself.
Mm-hmm.
They say k squared plus 172 is equal to x squared,
Mm-hmm.
and then you get x squared minus k squared is equal to 172, and x plus k times x minus k is equal to 172. So then you know that
I
uh
feel like you have made too many variables.
uh yeah, because I kind of did do a, because what I did then was say that x plus k and x plus k and x minus k must be uh factors of 172.
Mm-hmm.
Because 172 is 2 squared times 43, and x plus k must be greater than x minus k.
You've gotten the answer, so somehow you have done it, but I feel like the way you're doing saying it right now is not perfect. So what you can
Oh,
do here is, let's say we have positive integers j and k such that they are squares, right? You
yeah,
can say n minus 86 is k square and n plus 86 is j plus k square, right?
Yeah.
oh, yeah,
Because obviously it will be a little bigger than k, but we don't know whether it is 1 plus k or 2 plus k or whatever, right?
yes,
So then we can do the same thing that you are doing. We can subtract 172 is equal to k plus j square minus k square, and you will factorize it and say it is, or you will just simplify it and say it is 2jk plus j square, right?
yeah,
Now, if you think about it, this number is even, this number is even, so this has to be even,
yeah,
right?
yeah,
If j square is even, then j is even, right?
yeah,
So let's say j is some 2m, right?
yeah,
For some positive integer m. So then you are getting 2 into 2m into k plus 4m square is equal to 172, right?
yeah,
You can divide by 4.
yeah,
You'll get 43 here. You are getting mk plus m square is equal to 43, but 43 is prime. So this is over.
uh,
Then you are guaranteed that m is 1 and k plus m is 43. So k is 42.
yeah,
And this is a much easier way to do it. And j is 2, obviously. So k is 42, j is 2. So it is 42 square and 44 square, right?
uh, yeah,
Correct.
yes,
Yes.
So getting the answer is important, but it's also important to show the proof properly. Like you cannot be like, "Hey, I kept doing x plus j minus x square and all, and now you're confused." right?
Yeah.
See, senior Olympiad, when you're trying, you'll have to show the proof perfectly. Then you will get full marks. You have already gotten the answer, so it will be a shame if you lose points on that.
Yeah.
It's not enough to get the answer by guessing and all. You have to show the proof properly. So then go in a step-by-step manner, make some simple assumptions like some square, then some other number plus that number square will be the higher one.
Yeah.
After that, we use parity, even, odd to figure out this stuff.
Mm.
Okay, which one else did you get the answer? Any answer?
Question 4, I think there's no solution.
1 second. Question 4, there is no solution. There are no integers n for which it is a perfect cube. But okay, what is the reason? The question is saying, are there integers n for which 3 power 6n minus 3 plus 3 power 3n minus 1 plus 1 is a perfect cube? What's the reason?
So like first you say 3 to the power 3 and minus 1 is equal to x.
Mm-hmm.
So then you get that x cubed plus 3x plus 1 equals to like some integer k cubed.
Wait 1 second. If you're calling it x, you're doing x cube. Why are you doing x cube right now?
Oh no. I was talking about the 3 to the power 6 and minus 3 will become x cubed.
It's not going to become x cube. It will become 9n minus
Oh
3.
wait, what did I
No,
call? Oh no, I made x equal to 3 to 3 to the power of 2n minus 1.
okay, then this is x cube plus what should we do to get this?
Multiply that by 3.
N.
You have to multiply it by 3 to the power n. But I don't think that was what you have done.
No.
So you're miscalculating and getting some weird things. I don't know how you're getting the answer.
Uh,
This is not a perfect cube, but the logic is not correct. So figure out the logic first. Adam, have you tried anything here?
Yeah, so I try letting x equals 3 to the 3n minus 1, and then you get a third times x squared plus x plus 1.
Wait 1 second. If you call this as x, what are you saying about this?
That is 1 over 3 times x squared.
X square would be 6n minus 2
Oh
by
no, you let
3.
x be 3 to the power of 3n minus 1.
That only I have written. No?
Oh, yeah.
X square would be 3 to the power 6n minus 2. So it will be 3 to the power 6n minus 3 into 3, no?
Uh, um, oh, wait. Times x squared.
Why will it be 1 by 3? 1 by 3 x
Yes,
square would be wrong.
times 3, yes.
1 by 3 x square would become, wait 1 second. Oh wait, no, I'm only wrong. X square would be what? X 3 to the power 6n minus 2 divided
Yes.
by 3 would be minus 1. Okay, it is correct. 1 by 3 x square, not
Oh, yeah.
this.
Okay, and then I said plus x plus 1, and I got that as a cube. So I tried using the fact that it has to be non-zero or negative 1 mod 6, and the fact that x is a power of 3, but that didn't really
You are
help me.
saying that this is a perfect cube. You're assuming. You're
Well,
assuming that it is a perfect cube and trying to find n.
yeah,
You have to be clear about what you are doing.
yes.
Uh,
So if we can find x, we find n, and we have that x is a power of 3, but I didn't know how to get what to do after that, really.
okay. Okay. Uh, if you look at this expression, what happens if n is negative? What happens to this whole thing if n is negative?
It becomes a
This is
frac-
negative, this is negative. It will be fractions, right?
yes,
Yeah.
Some fractions which will never like be a perfect cube then.
no,
For n less than equal to 0, for example, if you try -1, or even if you try 0, what happens? 3 power minus 3 plus 3 power minus 1 plus 1. So 1 by 27 plus 1 by 3 plus 1. And basically, it's not going to be a perfect cube because it is not even an integer.
yeah,
For n negative, there is no chance of this being a perfect cube, right?
yeah,
Yeah.
So we have to only figure out what happens for n positive. And we will use the squeezing method that we have seen earlier. We'll try to put them between two positive cubes, two consecutive cubes.
oh, okay,
Okay.
For example, I know that 3 to the power 2n minus 1 whole cube is equal to 3 to the power 6n minus 3. And that is clearly less than this number,
yeah,
right?
Yeah.
If I can get the next cube and prove that the next cube after this is bigger than this number, that's it.
yeah,
I have some x cube. I need to show x plus 1 cube is bigger than this, right?
yes,
So all I have to do is try to find out what is 3 power 2n minus 1 plus 1 whole cube. Correct?
yes,
Let's calculate it by our formula a cube plus b cube plus 3ab a plus b. So this is 3 power 6n minus 3 plus 1 plus 3 into 3 power 2n minus 1 into 3 power 2n minus 1 plus 1, right?
yeah,
So this is becoming 3 power 4n minus 2 plus 1. So 4n minus 1 plus 3 power, this and this multiplied become 3 power 2n plus 1 plus 3 power 6n minus 3, right?
yes,
Yeah.
So now we just have to show that what we have here is smaller than this, correct?
oh, yes,
That's not very hard because two terms are anyway matching.
Yeah.
yeah,
We just need to show that this is smaller than this plus this, right?
yeah,
Yes.
So let's just think about it. It is 3 power 3n by 3. So, and this side is 3 power 4n by 3 plus 3 power 2n, right?
yeah,
Yeah.
The way to prove which one is bigger is just take this minus this and check whether it's positive or negative, right?
yes,
So I will just do 3 power, it will be becoming 3 power 4n minus 3 power 3n by 3 plus 3 per 2n. Clearly, this is positive, this is positive.
Yes.
When I subtract this minus this, I'm getting positive. So
Yeah.
obviously, the second two terms are larger than this,
Yeah.
which means
Yeah.
that our desired expression has been placed between some cube and the next cube.
Yeah.
Yeah.
That's how you prove something is not a perfect cube, not a perfect square. You cannot do it by randomly assuming x and doing random things. And definitely modular arithmetic is not going to save you here, because there are so many things to consider. If you try to do it by like I will figure out mod 2, mod 4, or mod 7, it's not going to work very easily, I think.
No.
Like we know that all the perfect cubes have to be certain things mod 7, but
Yeah.
like figuring out mod 7 here is, I mean, that is also a possible approach, but why didn't you do it then? We have learned
Uh,
in the theory, right, that all of them have to be something mod 7.
yeah.
Actually, the problem is that if it is not 0 or 1 plus, it has to be 0 or plus minus 1 mod 7. So you
Yeah.
have to figure out whether it is 0 or plus minus 1 mod 7. But the problem is that that is not a foolproof method, because even if it is that, it's not guaranteed to be a cube.
Yeah. That was problem.
The problem is that it's not sufficient. It's necessary, but not sufficient.
Yeah.
Every mod plus minus 1 mod 7 number is not a perfect cube.
Yeah.
So in all the problems where you have to prove something like this, that's a bad strategy to try to use. It's not even going to give you a proof. Do you understand what I'm saying?
Yeah.
Yes.
What happened to 2 and 3?
Uh,
Anything in 2 and 3?
Uh. Mm,
Okay, let's look at question 2.
okay.
Find the sum of all integers n for which n minus 3 and n square plus 4 are both perfect cubes. Okay. Sum of all the integers n for which this and this are both perfect cubes. So anything have you guys tried here? Anything?
Um,
uh,
well, I was just taking like modulars, but I didn't really get anywhere.
I,
You
I
have
let
to, hmm?
I let n minus 3 equal to k cubed,
Hmm.
and then you have that k cubed plus 3.
Is n
Oh yeah, n k cubed plus 3 all squared plus 4.
is also a
But
perfect cube.
yeah, but then if you try to simplify that, you get k to the 6, which is nice.
3 power 6 plus 2 into 6 k cube. plus 9 plus 4, 13 is a perfect cube.
Yeah.
So this is anyway cubes and all. Plus 13. So okay. Plus 13. So k cube common here, you're getting k cube plus 3 or plus 6. K cube common, k cube plus 6 plus 13 is j cube. Okay, it is giving us something, but I don't think it's enough. If you think of modulo now 7, it has to be 0 or minus 1, plus minus 1 for each of the cubes.
Yeah.
But there are too many cases.
Yeah. You won't be able to find all.
I mean, you'll have to do so many choices because k could be any 3 and j cube could be any 3.
Yeah.
Yeah.
So it will be annoying to do that. But a few cases we can definitely say, for example, if k cube was plus minus 1 mod 7, then k power 6 is guaranteed to be plus 1. Plus 6 times plus minus 1, right? And this is minus 1, right? This is
Yeah.
what I'm getting on left hand side, right? Mod 7.
Yeah.
So you can see that if it is plus 1, it is becoming 7 minus 1. If it is, so notice that you're getting 1 plus 6 minus 1, which is fine. But if it was 1 minus 6 minus 1, it is also fine, right? Minus 6 is also fine. Yeah.
Yeah.
Both cases are fine, but in both cases, you are getting, in this case, you are getting j cube is minus 1. In this case, you're getting j cube is plus 1.
Yeah.
Okay, but that doesn't give us any new information. So one thing we know is that when k cube was plus 1, j cube is minus 1. When k cube is minus 1, j cube is plus 1, right?
Yeah.
Yeah.
So they are alternating. The other thing is if k cube is 0 mod 7, you're getting j cube is minus 1 mod 7,
Yeah.
right?
Yeah.
Yeah.
Okay, so we had said that if k cube is 1 mod 7, can we say something about k? We can't because k could be many choices.
No. Yeah.
That is the issue because you're here to find something about n, you need k.
Yeah.
For any one possibility, k could be many different modulo 7.
Yeah.
That's why you should not be doing this method. There are too many cases possible. You have to do something with the expression, something with algebra. If this and this are both perfect cubes, can we say that their product will also be a perfect cube?
Yeah.
Product is also a perfect cube. So we can say n minus 3 times n square plus 4, which is equal to n cube plus 4n minus 3n square minus 12, which we can simplify and say n cube minus 1 minus 3n n minus 1. So this will give us minus 3n square plus 3n. and plus 3n I'm getting, so plus n is left, and I'm already getting a minus 1, so I need a minus 11 here, right?
Yeah.
Basically, I'm just simplifying it because this is clearly n minus 1 whole cube plus n minus 11, right?
Yeah.
So what we are getting is the product, which is a perfect cube, is looking like this, right?
Yeah.
Okay. Also, the product can be written as, we have written it like this here. So we can write it as n cube minus 3n square minus 4n plus 12, right?
Yeah.
Another way to think of the product is this, correct?
Yes.
What is the nature of this quadratic? 16 minus 4 into 3 into 12. The discriminant is less than 0. What does it mean?
There's no real root.
So what is it? Positive or negative always?
Negative.
The quadratic 3n square minus 4n plus 12. Will it be always positive or always negative?
Always positive.
So that is important to realize that we can see from the discriminant itself. And if it is always positive, we know that this product is n cube minus something. So it is less than n cube, right?
Yes.
And here we got what? It is n minus 1 cube plus something,
Yes.
right? As long as n is greater than 11, this is positive, right?
Oh, yes.
As long as n is greater than 11, the product is lying between the two cubes.
Yes.
And then it's not possible
Yeah.
because products should be a perfect cube, but it is lying between two successive cubes. Correct?
Yeah.
So for n is greater than 11, it's not possible for it to be a perfect cube,
Yeah.
right? So
Yeah.
there are no solutions for n greater than 11, right?
Yes.
Do you understand how we have gotten to here?
Yeah.
Okay. Now that part is done. No solutions for n greater than 11. We know that our product is less than n cube for sure. What else can we say? So we have seen n minus 1 cube plus this thing. We have n cube minus 3n square plus 4n, I think, minus 12. That is our thing. Minus 12. That is our expression.
Yes.
Which is the product P. Now, what is n minus 2 cube? Let's look at that. That is n cube minus 8 minus 3 into 2, 6n into n minus 2. So this is n cube minus 6n square plus 12n minus 8, right?
Yeah.
Yeah.
So I want to compare this number with this number. So I can see that n minus 2 whole cube is equal to n cube minus 3n square plus 4n minus 12. And I have to subtract from there minus 3n square. minus plus 4n, so I have to do plus 8n I have to do. So I should do minus 3n square minus 8n.
Yeah.
And I already have minus 12 here. I need a minus. So I have to do plus 4. So I should do minus 4.
Yeah.
Right?
Yes.
So what I'm saying is n minus 2 whole cube is equal to p minus this thing.
Yes.
Right?
Yeah.
Now, this thing that we have here, what this means is that n minus 2 whole cube will be less than p if this is positive, right?
Yeah.
Correct?
Yeah.
So this is easily factorizable, by the way. Minus 12 minus 2 minus 6. So if you factorize it, you get 3n square minus 6n minus 2n minus, no. It is not easily factorizable. Minus 8n I have, and I need to make it 12. Minus 12 I need to make, that's the issue. I'm getting a plus 12. Okay. So, right. So it is not easily factorizable,
No.
but but we can make a guess about when it is positive. That we can do by finding the roots of this. So roots of this are what? Minus b plus minus root over b square 64 minus minus plus. So 64 plus 48 by 2 into 3. You're getting 8 plus minus root over 112. So
Yeah.
112 by 6. And that is 4 can be cancelled. The 2 can be cancelled. 4 plus minus root over 28 by 3. Right? So root 28 is like 5 point something. 4 plus minus 5.3, let's say, by 3. So it is like one root is near 3 point something and the other root is negative 0.4. Right? So the quadratic will be positive beyond the roots, right?
Yeah.
Yeah.
So if you are below negative 0.4, then this is positive, right?
Yeah.
So basically, if n is less than equal to minus 1, correct? In that case, we can say for sure n minus 2 whole cube will be less than p. Correct?
Yeah. Yeah.
And we already know that we had gotten earlier
And
that
yes.
p is greater than, no, we can compare p with n minus 1 whole cube also. We had already done the comparison for n greater than 11 earlier, right?
Yeah.
We had written p and compared it with n minus 1 whole cube. So let's do that comparison. So p is equal to n minus 1 whole cube plus n minus 11, right? This is what we had gotten earlier. Do you remember? This is what we had done earlier.
Yeah.
So if n is less than minus 1 or less than equal to minus 1, then what can we say here? This is a negative thing then, right? So P is going to be smaller, right?
Yeah.
Do you see what I'm saying?
Yeah.
Because you're adding a negative thing to this to get to P, right?
Yeah.
Here we have already gotten that if n is less than equal to minus 1, P is greater than this.
Yes.
Now we are getting P is less than this.
Mm.
So that means P, which is supposed to be a perfect cube, is not possible, right?
Yeah.
Do you understand what we are doing?
Yes.
Yeah.
Earlier we compared P with n cube and n minus 1 cube or something like that. Now we are doing with n minus 2 cube and n minus 1 cube,
Mm.
right? And here we got that n cannot be greater than 11. Then P lies between them, right?
Yes.
Now we are getting n cannot be less than minus 1 because then P lies between these two.
Yeah.
So we have eliminated two big portions of the number line. N cannot be less than minus 1, n cannot be greater than 11. Right?
Mm.
So the solutions for n should lie between 0 to 11, right?
Yeah.
And now we are done because we have only 11 choices and there are very few ones which n minus 3 and n square plus 4 are cubes.
Mm.
If n has only 11 options, it's so easy to get the answer now, right?
Yeah.
Obviously, you can say that n minus 3 is a cube for 2 minus 1, it will become is a perfect cube. 2, 3, 4, and 11. Right?
Yes.
And n square plus 4 is a perfect cube only when n is 2 or n is 11. Correct?
Mm.
So the common solutions are 2 and 11, right?
Yeah.
Yes. Yes.
The answer is 13, which is the requested sum of possible solutions. So notice in the previous question also and in this question also how we are using the squeezing method.
Yes.
We are always saying if you want to prove cubes or squares, try to put it in between consecutive cubes. Here we took our expression and we cannot do anything directly, just n minus 3 and n square plus 4. We said that if both are cubes, the product is a cube. And why did we do product? Because product gives us terms like n cube.
Yeah.
On their own, they are linear and quadratic terms. If you do multiplication, it becomes a nice cubic term. Then you can compare with nearby cubes. Right?
Yeah.
Okay. Question number 3. It says, are there triples PQR of primes for which P square minus 7, Q square minus 7, R square minus 7 is a perfect square? We need to find PQR, which are prime numbers for which this product is a perfect square. Okay. Right. So product has to be a perfect square. So product should be positive, right?
Yeah.
Uh, let's think about it. By the way, they have to be prime numbers. Prime numbers are like numbers from 2, starts from 2, 3, 5 and all. Other numbers are okay, but 2 is a special prime number which is even, right?
Mm.
So we should check that first, whether 2 can be any of this. If one of them is 2 and others are not 2, then the overall product is negative. Think
Yeah.
about it. If one of them is 2 and others are not 2, overall product is negative, right? And
Yes.
if all 3 are 2, then also overall product is negative,
Yes.
right? So
Yes.
those cases are not possible. One of them is 2 or all 3 are 2, right?
Yeah.
What if 2 of them are 2? 2 of them are 2 and one of them is not 2. In that case, you will get -3, -3, 6 into something, right?
Yes.
And now think about it. This is, if R is not 2, R will be an odd number, odd prime, right?
Yeah.
So R square minus 7 is going to be even,
Yeah.
correct?
Yeah.
So if it is even, you are getting R
Would it
square
not
minus
be
7.
would it not be 9 times R
It
squared
will be
minus
9 because it
Yeah.
is 3 into 3. So 9 times 2k we are getting, right?
yeah.
So it is 18k, which is like uh, basically it is 2 mod 4. 18 is 2 mod 4. We don't know anything about k though. One second.
Really, you need R squared minus 7 to be a square because 9 is a square.
R square minus 7 should be a square because 9 is a square, right? The
And then
product has to be perfect square. So R square minus 7 should be a square.
and there's only so many R's in
Yeah.
check.
No, but there are many prime numbers. No, you cannot check all of them. What do you mean only so many?
No, because R squared's a square, so eventually the difference between two squares will be too big. Like R will have to be pretty small.
Uh,
Like 16.
see, if two of them are 2 and one of them is an odd prime, we are getting the overall number. There is no issue here actually because k is odd. We
Oh,
cannot get uh, are we guaranteed that k is odd?
mm,
R is a prime number. R square minus 7. We are subtracting two prime numbers. It will be even. but it cannot have factor of 4, no? Like,
one more calculation geometry.
see, there is no power of 2 here, right? It is a 2k plus 1, like this, something like
yeah.
this.
Yeah.
Yeah.
It cannot be that k itself is even. I don't think. 1 second. Can it be 4k plus 1? 4k plus 1 minus 7. Is a prime possible with the form 4k plus 1?
Well, the
Um,
square number is
Square number is possible, but it's a right. There will be primes like that, I think. 41 and all is possible. Okay, it is possible to be 4k plus 1, but oh wait, I'm still missing the idea because okay, let's say it is like this. What am I getting? So it is giving 4k square plus 4k plus 1 minus 7, right? Okay, now it's done because this is R is odd for sure, right?
yeah.
So I'm getting this perfectly. This is correct. So you're getting 4k square plus 4k minus 6, which is of the form minus 6 mod 4, which is 2 mod 4, right?
Yeah.
2 mod 4 is not a perfect square.
No.
Basically, R square minus 7 is coming as 2 mod 4.
Oh, yeah.
yeah.
The point is, this happened when two of them were taken as 2 and the third one was in general, right?
Yeah.
So 2 mod 4 times 9, that doesn't affect modulo 4, by the way, right? 9 doesn't bother us because 9 is 1 mod 4. So product
Yeah.
is still 2 mod 4 when you take difference. So it doesn't work because the whole product is not coming as a perfect square form, right?
Yeah.
So that means we have done the case that 2 cannot be ever one of the primes. We have done the case that there was 1, 2, 2, 3 2s and 2 2s, right?
Yes.
So now we are saying that it has to be odd prime numbers and the product has to be a perfect square.
Yes.
We know that P, Q, R are odd and they are primes.
Okay.
Basically, we have handled the case of 2. Now we are looking the odd cases. So now write let's think of how to write P square, Q square, and R square. Again, we'll do the same thing. P is 2k plus 1 whole square. So you can say it is 4k square plus 4k plus 1. So we can say that it is 4 times some integer plus 1, right?
Yeah.
4a plus 1 we can say, if you want. A is an integer, this integer, right?
Yes.
Similarly, this is p square by the way.
Yeah.
I said p was 2k plus
Yes.
1. So p square is coming like this, right? So p
Yes.
square
Yeah.
is 4a plus 1, q square, and let's do the 4b plus 1 minus 7 and 4c plus 1 minus 7, right?
Yeah.
So we are getting again 4a minus 6, 4b minus 6, 4c minus 6. Taking modulo 4, we'll get minus 6 is basically plus 2. We are getting plus 8, which is a 0.
Yeah. Also got that.
0, I don't think is possible.
Um,
Is possible 0 mod 4? Yeah, it is
Yeah.
possible.
yeah, it is.
What are not possible? 2 and 3, right?
Yeah, those aren't.
What did I say in the beginning? Which ones are possible?
0 and 1 mod 4 are squares, and 2 and 3 mod 4 are not squares. Or 0 and 1 mod 4
2 and
can.
3 modulo 4 are not a perfect square.
No.
Right. So here, what are we getting? Let's check once more. It is 4a minus 6, 4b minus 6 like this. So we can take 2 common from each of them. We're getting 8, 2a minus 3, 2b minus 3, and 2c minus 3, right?
Yeah.
This is odd, this is odd, this is odd, right?
Yeah.
Because even minus odd. And
Yeah.
this is power of 3, right? So it can never be a perfect square, no?
Mhm.
Do you see why it can never be a perfect square?
Oh. Yeah.
Because the prime factorization here has 2 power 3 and there's no other factor of 2 ever coming.
Yeah.
We have proved that p square is of the form 4a plus 1 because we took p as an odd number.
How do you know K isn't even?
Huh? It doesn't matter because look at this.
Oh, yes. It might matter.
Doesn't matter what k is. We just take 4k square plus k, 4a plus 1. This is an integer.
Yeah.
P square is basically 1 mod 4.
Yeah, I see.
P square is 4a plus 1. So 4b plus 1, 4c plus 1. We got something like this. We took 2 common out, 8 came out, and then these numbers are guaranteed to be odd. So the
Yeah.
only powers of 2 are 3 powers only. And then it can never be perfect square. Right?
Yeah.
Okay, so till question 4 we have discussed. 5, 6, 7, 5 to 11. You have to still try. And there are some more problems that I have to discuss. So try it once more, give it a try, see how much you can do. Notice that the number of techniques are limited only. It's not like we are doing many different methods.
Yeah.
Yeah.
It's a limited set of techniques, 2, 3 techniques only are there. You just have to apply it in different ways. That's what you're supposed to learn. And this type of question comes a lot. All of these are some problems from some papers and all. Many of them are problems from some papers. So try it out, see if you are able to do it. We'll discuss on Sunday these remaining ones.
Yeah.
Yeah.
Don't come without trying. Try it definitely and then come
Yeah.
to class.
Okay.
Okay, fine. That's all for now.
Yep. Thank you.
Mm.
Okay, thank you.